to
This
you what
conference will now
FPGA
be
is.
recorded.
So can someone like unmute yourself and like tell me what is your understanding about FPGA? See, sessions has to be interactive. I would like everyone to be interactive.
Hello, sir.
Yeah, tell me.
So what I understood is that it is basically an IC which can be programmed to perform
Mm-hmm.
specific operations for an application.
Okay. Yes. Good. What about
Yes,
others?
sir. Hello.
Yes, Kiran, tell me.
Sir, without implementing hardware, we can test the code in FPGA. We can dump and we can test the code.
In the context of ASIC, right? You're right. Yes. Any other answer? What about others? Come on, like it has to be interactive, please. What is your understanding? When we say FPGA, you must be knowing something, right? So tell me what you know about FPGA. Okay, let's get simply, please be interactive. So this session has to be interactive. That's what I expect. See, the FPGA, as the FPGA name FPGA indicates, field programmable gate array is so right. So field programmable gate array is like somebody said, it's a IC, right? So it's a chip that can be programmed to do many things actually, like so that same field programmable gate array, you can design it as some communication system, or you can design it as some medical equipment, whatever the things you want to do. So it's kind of like, see, the name itself indicates it's an array of gates, right? So it can be AND gate, OR gates, or logical uh, uh, like flip flops, many things. It's an array of gates, and that array of gates can be programmed in the field. It's not something like in the ASIC you are fabricating, right? So in the fab you will be fabricating that IC, and like it's not something like that. IC functionality you cannot change, like for instance, like in your mobile, some Snapdragon chip is designed, and you cannot change the basic functionality of that Snapdragon on the field. I mean, once it is delivered to customer, you cannot change the functionality. But this IC functionality, the digital functionality of the entire IC can be changed in the field. That that is the meaning of that field programmable, right? So it's something like you can think of like the Legos. I mean, in the childhood, you might have played that like puzzle game, right? So you will have multiple blocks, and you can build the way, you can shape that Legos in the way you want, right? So in the same way, this field programmable gate array is something like we can design a digital circuitry on the field. There are many misconceptions about FPGA. I mean, in terms of job perspective, as well as like in terms of technical aspects and the usage of that. Maybe we will in this session, like main objective of that is to resolve that misconceptions, right? So as I was saying, it consists of array of logical gates, and it can be connected together to make a circuitry which you want. Okay. So when I say configurable logic gates, in the sense, it's actually entire FPGA. I mean, in the general terms, we say it's a gate arrays, right? But actually, it's like something like it's a logical cells. Okay. To be more specific, it's kind of memory cells. Okay. So like there are various different types of FPGAs, like fuse FPGA, SRAM based FPGA, flash based FPGA, and in general you can think of it's like kind of memory bits, memory cells. Each logical cells, it's kind of memory cells. like a lookup table. How you program that lookup table will constitute a circuitry what you want, right? So that logical cell, for instance, you can assume it's like some small logical cell. I mean, you don't think about full FPGA IC, which consists of millions of logical cells. You think of a small logic cell. Uh, the same logic cell can be programmed into a AND gate, or it can be programmed into a NOT gate, or it can be programmed to any gate. So it's something like maybe we will start with a very simple example. Whatever I'm drawing on the screen, is it visible to you all?
Yes, sir.
Yes, sir.
Yeah.
It's visible.
So we will consider an example of two input gates, any gate. Okay. So A, B, and Y. Okay. So I will say that like it's 0, 0, 0, 1, 1, 0, 1, 1. Okay. So this is possible input values for a two input gate, right? So now this particular Y, right? So if it is an AND gate, it will be 0, 0, 0, 1. If it is OR gate, it will be 0, 1, 1, 1. So on. I mean, based on the gate, this Y it is going to change, and possible combination of inputs remaining same, right? So I'll be having same input possibility combination. So if I say in terms of system, it will be something like this. I have a black box. I have two inputs, A and B. And I have one output, Y. So you can assume this as a memory, okay? So it's a simple a two-bit memory. I mean two-bit address memory. So in the two-bit address memory, possible locations is basically 4, right? So if I program this memory as 0, 0, 0, 1, so it will act like a AND gate, right? So whenever A00, this memory address is 0. So 0th data is something like 0. That output you are going to get here. If it is 1, 0, again 0, 0 output you are going to get. It's something like accessing the memory, right? So this memory, I mean, if I ask you, is this memory is modifiable? Is it like, can I edit this memory data? I mean, in the, you can consider it's like something like SD RAM or like your SD card. So this 4 location, can I overwrite anytime? Yes or no? This is a memory, right? So memory, small memory block, and this memory block I can write anything, right?
Yes, sir.
I can modify in the field. So this is something like one logic cell we call in the basic building block, the configurable building block of FPGA, that is called lookup table. So this is how we design the circuitry in the FPGA. Basically, we are modifying the contents of these logic cells. Okay. So if it is like 0001, so this particular logic cell will act like a AND gate. I mean, internally it is a memory. It's a SRAM based memory, but we are modifying that memory into like we are configuring. That's why the name configuration. We are configuring this memory for various values to act to make that memory cell like a logic gate. Okay. So using the same memory, if I want to make it like a NAND gate, can you tell me what the content? What content should I write here? If I want to make this memory as a NAND gate, What content should I
One,
write here?
1, 0.
Right, 1110. So if I replace this content as 1110, then this circuitry, this lookup table will act like a NAND gate. So see, this is a simple example, but in the actual FPGA scenario, like you might have heard about Xilinx FPGA or Quartus FPGA, it is not 2 input. Usually it will be 6 inputs, right? And we have the cascading logic where you can make it like higher inputs also. So for instance, if you want to design a big uh, ripple carry adder, or like a 6 input ripple carry or adder, or any complex circuitry, digital circuitry where you have 6 different input, just you need to modify. I mean, you need not bother about like what circuitry, what gates you have to use. You just need to see, whenever I say 6 inputs, how many possible combination you will have? 2 power 6, right? It is a 64 combinations you have. 64 combinations in the lookup table. You just need to see what are all those 64 bits in the lookup table, that is y. What are all those 64 possible outputs that particular circuit to make that circuit. I mean, you not I mean, in the actual hardware, what do you do? So you should, I mean, if it is like, if you want to design a 64 bit 6 input based circuitry, like with the ripple carry order adder or subtractor, then what you do, you actually like uh, synthesize those complex digital circuitry using TTL or logic gates, right? Multiple logic gates. But in the FPGA, we will be bothering only on that output LUT, that is Y part of that. What should be the output for the given six inputs? Okay, so it's something like just a black box we are bothering, right? And that too, I mean, many people will be scared that like, okay, if I want to like in the for instance, like in the PD case, right? So if you want to design any circuitry, like you have to design, maybe there are like libraries available, but other than that, like you have to design individual components. But here, once you write the RTL, that VSDL, most of the mapping, right? So whatever the logic inference will be there from that VSDL or Verilog, that will be taken care by tool to map to these memories. So these lookup tables will be not just one or two, millions of lookup tables will be there in the FPGA, right? So that mapping or configuring that FPGA to act like circuitry what you want will be taken care by tools. Xilinx, or like Xilinx is recently acquired by AMD. Altera was like once upon a time, it's a pioneer in FPGA industry. Now it's acquired by Intel. By this itself, you can understand the power of FPGA nowadays. Like all the high-speed computational, even high-speed telecommunications like 5G, what we say like now upcoming 6G in the 2030, these are all like based on FPGA based designs. I mean, not I'm not saying about the UE side in the sense like your mobiles, that is like user side, right? So where like millions of chips you are going to produce, but wherever base stations are there, that usually we build using FPGAs, because now today it's a 4G, or like now in few months 5G will be there everywhere. Once that is done, what will happen is like 6G is going to come. So when we are transitioning towards 6G, what will happen, like if it is like a fixed circuitry like your ASIC, then the modification or like the infrastructure uh, effort required will be huge. I mean, the amount of investment required is huge. So what they do is like they'll put the FPGA based architecture. Whenever the infrastructure gets changes, they just need to modify, or in the field they need to update the circuitry of the FPGA, the digital circuitry or algorithm what they have built. They just need to upgrade that, right? Any questions here? And that too, actually, like this is one NAND gate, right? So, and I said 6 input. So if for instance like you have another NAND gate, here one more LUT will be there where you maybe like you made act like a OR gate. And now internally, right, we will have switching matrix. We say it as a switching matrix. So this switching matrix also is a configurable thing. Okay, so if you want to connect from here to here, we basically configure this program, this switching matrix. So this is also programmable so that it will be connected to each other. So everything will be taken care by tool, but we need to understand first like what actually like can someone mute somebody? His voice is actually echoing. What exactly? Why do we need? I mean, how exactly this implements also is very important. I mean, when you design a complex circuitry, optimization understanding also it's very necessary, right? So I think few questions. Arjun is saying, so basically FPGA main advantage, it can be modified. Yes, the circuitry can be modified anytime in the field, right? So that is the main advantage here. And compared to like your processor, I mean, like whenever I am comparing with respect to ASIC, we say it is a modifiable. But there is another benchmark. So is also the FPGA will be also used as an alternative to your GPUs or CPUs, right? Uh, so so actually, like when we say that comparing with respect to software, GPUs or CPUs, there everything is parallel, right? I mean, in the FPGA, everything is parallel, in the sense like in the CPU, what we'll do, like we will fetch, decode the instruction, and we will push into ALU, and like there are quad core mechanism or octa core multi core mechanisms, but again, that is limited to that many cores only. It's not something like how it is in the real time way, like hardware it is happening, right? So for instance, let me take an example of FFT. So in FFT, what is going to happen, like we have to actually like go with that butterfly mechanism. If you write a simple C code based mechanism, if you implement it in the processor or GPU, so step by step in the flow way you can make it, right? So it's not something like in one clock cycle itself you're going to get the output. One after the another instruction you can fetch it and decode, and you can do those computation. But whereas here in the FPGA, you can design the digital circuitry, equivalent digital circuitry of that entire FFT itself, and make that circuitry maybe like within a few clock cycle compared to your GPU or CPU. Nowadays, if you see artificial intelligence companies or data centers, now people are starting using FPGA rather than GPUs and CPUs. I mean, that's where like now FPGA engineers demand is growing like anything. I mean, after artificial intelligence and especially like ADAS and applications like 5G and 6G. Because of that, like now, if you just search FPGA in the LinkedIn, right? So in the Bangalore itself, you can see like thousands of openings compared to any other domain, VLSI domain, because it's a scarcity. I mean, there's a misconception that like it's not a VLSI domain, and many freshers will not get into that. And there are like very few FPGA engineers in the market, and demand high actually for the FPGA nowadays. And they'll be actually like I mean, in my experience, we are hiring FPGA engineers compared to like what like ASIC engineers, right? We'll be paid more compared to ASIC. Like so, one more thing is like little knowledge of. See why I like, basically like let me tell my story. Why do I like FPGA ASIC FPGA compared to ASIC is one reason actually. Like see, even though I got, I mean, like multiple times I got many basic opportunity, I denied. That is main reason behind that is, see FPGA, right? Whatever the things we work, it's a kind of system level, right? So for instance, like if I was giving you an example of previously for the Samsung, I was working for the 5G systems. So there, whatever the things we implement, we can see it as a system, right? So I mean, it's like a system level thing, like a 5G base station when I'm seeing saying. So we have to program that and like test in the system level, like in the sense like as a whole 5G base station we will be working. But whereas in ASIC, you'll be working as a small modules, or like maybe that realization may be like limited to that chip only, right? So it may not be like something like so for instance, Qualcomm is developing Snapdragon. So in the in that scenario, like what you will be see at the end in the Qualcomm as a engineer, you'll be seeing end product maybe that chip itself. You will not see like how that mobile will be developed and deployed, right? But whereas in a FPGA, whatever the system I develop, I'll be seeing as the end product itself, right? So it's not something like I'll be limited to that chip itself, because FPGA as a chip, it's already developed from the ASIC engineers, or like a physical design PD. All this flow has gone through as a FPGA, and it has been already developed. But our job is to write a Verilog code and implement it on that and make a system rather than just a chip or something like that. I mean, again, there are multiple domain. I mean, like as a FPGA engineer, you can work as a chip engineers also, that we will get into that, like how exactly it's been how it's been classified. uh, there are some questions like FPGA is high costly, but compared to IC we design using physical design, but why do we still use, right? So that is a catch actually. So for instance, whenever I say like ASIC flow design, so that chip will become like cheaper only if you are actually producing in the mass production, maybe like some 1 lakh quantity or 2 lakh quantity. Like if it is a mass production, then only it's going to be very cheap, right? The amount of time required to develop that, right? So I mean, how many like hundreds of engineers for single chip they will be working, right? So because if you make any mistake, it's not a correctable there. I mean, you have to go through like lot of verification effort there, lot of physical design, STA, like CDC linting, everything. You have to like go through the proper flow, and you have to make sure that like not even a single mistake in that IC. And when you go to the production, if there is any mistake, it's actually like everything has to be like refabricated in the chip. You cannot just like correct it like how we do it in the FPGA, right? So if you compare that cost, like I mean in the mass production cost, then FPGA will be cheaper only. Because for instance, let me consider an example, like we are developing some communication system for like some defense application. uh, the numbers there, right? It will not be something like thousands. So maybe 50 units or 100 units, like some like let me consider best example is base stations. So how many base stations are there in India? Maybe like in some, like for instance, like let me consider example of Geo itself. So they may be deploying some thousands of base stations, right? So not in lakh actually. Like when we say that like your ASIC based designs like Snapdragon and all, so that will be produced in millions of ICs, right? So not in like hundreds of ICs. So once they deploy that Snapdragon, it's a millions. But when we say that like base station based application, so it's unnecessary effort actually. Like the amount you pay to the uh, like verification engineers, physical design engineers, it will be huge. I mean, if I consider that cost, it's a negligible. I mean, it negligible when I deploy it on the FPGA. So I have to just buy maybe hundreds of FPGA. Like maybe like you can make a simple computation. So you have to maybe like just check like one chip design cost, maybe like something like 30-40 crore, right? I mean, because if you consider the amount you pay to the verification engineer, amount you pay to the physical design engineers, front end engineers, and fabrication, maybe in overall 30-40 crore. But when actually split across multiple ICs, it may come very cheap. I mean, it may be like some in few thousands. But now one FPGA, maybe like lower end FPGA, will cost something like very lower end. If I consider, it will be like 12 to 13,000. I mean, zinc SoC, very I mean very basic FPGAs, you will get it for 2,000 3,000 also, max CPLDs and all. So if I consider that cost for the hardly for the 50 or 60 units, it will be maybe like within 2-3 I can finish it off. It's not even in the crore, right? So I mean, as an individual IC, when you look, you think it as a costlier one. But as a system, right? When you compute as a overall, see, actually, we will not be when we say that a product life cycle, we will not see a single chip production, right? So it's a overall cost. Like it involves like multiple engineers' effort, so many things. So as we compare overall cost, it's a very cheaper one. Again, Ranjan has like future will be FPGA eliminate ASIC physical design flow or demand of ASIC will be reduced. See, again, I mean, many people will confuse at this point also. It's not that like ASIC demand will be reduced. Okay. ASIC demand will be still there. So FPGA itself is an ASIC, right? So FPGA itself is an ASIC. So if you want to design a FPGA, you should know ASIC. So it's a trade-off actually, right? So whenever, again, like whenever you want to go for mass production, you will go with the ASIC itself. But whenever you go with the like limited number of units, like servers, a system which costs maybe like some few crores or few lakhs, bigger system, not consumer electronics. So as a consumer electronic application, still I say ASIC is a good solution, not FPGA. But a bigger system like communication systems or data processing systems, right? There we go for a FPGA based design rather than ASIC, right? Even for the ASIC flow also, right? ASIC flow also, whatever the RTL front end they have written, if they want to test it, like how their functionality is going to work, then they'll be tested on the FPGA itself, right? So, I mean, there is no other way. I mean, you cannot say that like I'm going to test my RTL or the functionality level testing once I get the final product. That is not going to happen. If there is any mistake in that final product, then you have to refabricate everything. But it's something like reconfigurable. If you make any mistakes, you'll be like keep on updating that and like you'll be modifying it. Okay, any other questions? Shall I proceed to next slide?
Yes, sir.
Yes. So benefits of FPGA over other technologies. When I say other technology, it is with respect to ASIC flow. Once if the functionality is not working the way I want, so I can just reprogram it, right? So we have seen like the one of the example what I have given is like the 5G deployment what we had done for the Samsung, right? So in the field also we faced like various algorithmic issues and things like that. So then like if it was a ASIC, then what you have to do, you have to go for the like complete reproduction of the chip, right? Here we just need to update that RTL, go for the bitstream generation and then just push it to the uh, uh, FPGA. Then that chip will act like the updated circuitry what you want, right? And speed. So this speed, right? So it's not with respect to ASIC comparison. See again, ASIC is faster than FPGA. I can agree because FPGA is something like kind of general purpose, right? So for instance, like even if you want to implement a simple half adder using FPGA, there will be a lot of unused what you say logic cells remaining, right? So power wise is still like what you say, it's not efficient way compared to your ASIC, where ASIC whatever the circuitry you want but for the particular application, you will be retaining that and rest you will not use it. I mean, you will not implement itself, right? But here it's kind of generic purpose. If I consider one FPGA, when I say I have something like 10,000 lookup tables, so even if I implement a simple AND gate or a complex one FFT algorithm, still that FPGA will be having 10,000 lookup tables. So there will be some methods where that lookup table will be unused, but still routing wise and all, it's not as simple as like your ASIC, right? But what you say that like, I mean, it's like again kind of trade off. So which to use, ASIC or FPGA, right? So based on the application and production. So but one thing I can say, it's there is no pain as such in like whatever the conventional ASIC flow where you have to do like a lot of physical design and verification. Here actually if you see in the FPGA based companies, there is like less requirement for the verification engineer, because even if it fails, there will be like I mean we'll be doing some simple functional verification, and like we will be running we do run some UM but not that extensive way, because if we find some bugs, still it's a correctable thing. I mean, it's not kind of like I need to spend a lot of verification effort, and like if it is like failing in some field, so still I can upgrade that software and I can get it the way I want to work, right? So it's not something like I have to reproduce entire hardware itself, right? So that is the advantage. So low power consumption, again, in terms of general purpose IC and GPU or CPU, FPGA can be made low power consumption device. But compared to ASIC, again, ASIC consumes low power because it has limited hardware, right? So again, it's all trade-off. You have to understand in that way which one to use. Customization is highly customizable. So I mean, very best example is ASIC. I kept on telling repeatedly. I'm telling that. So you can like you can modify the way you want, right? So it's not something like one-time programmable. It's a rapid prototyping. So even the ASIC design will be initially prototyped in the FPGA itself. If you want to understand how your ASIC design going to work, so you have to put it on the FPGA and then only you have to test. And even the DFT also, right? So DFT also, it's a FPGA based verification only. So I mean, it's not, I mean, it's all interdependent. You cannot say that like ASIC only or FPGA only or GPU CPUs only. So it's all interdependent. It has its own significance and its own value actually. Right now, I mean, it's like because of the scarcity of the engineers, like there, I mean, just go to the LinkedIn job portal and search FPGA. And one good thing you will notice that too, like it's not ASIC companies will be hiring, mostly system companies will be hiring FPGA engineers. I was saying that initially, right? So we'll be not ending our work just to the chip level. We'll be working as a system, as a product. When I say 5G based FPGA, I should know entire 5G system, how it works. As a communication system, if you are working as a FPGA engineer, you should know complete communication system. You should understand that complete communication system. That's where it's actually like very interesting, right? So you'll be hands-on working on that board. You'll know like how that chip is working, right? So you'll be working on the hardware, not something like just virtual things, right? So I mean, just not it is limited to tool. You'll be also going to the hardware and testing that. So next question is like how to program that. So it's again same front end between the ASIC and FPGA. It's same actually, right? So it's all hardware description language. So you'll be writing Verilog or VSDL or system Verilog codes, and you'll be converting that into bit level. Bit level, when I say initially, I shown you that LUTs, right? Lookup tables. So that lookup tables we will be actually programming. Okay. So that lookup table programming, what to program to that lookup table will be decided by your uh, what do you say, tools. Actually, you need not much bother. But when we actually synthesize, implement and place and route using tools, right? You do get STAs, I mean static timing violations. You'll get hold time violation setup, all these things you are going to get. You may see that like there is a high power consumption. Then actually like your physical design skills will come into picture. So whatever you had done in the physical design, right? How to resolve that like violation, timing violation, same techniques you have to use it here also. You have to go for some pipelining mechanism, synchronization mechanisms, so that you will make that violations, like make that design violation free, right? So usually we program that FPGA using JTAG or flash programming. So whatever the things I said, right? So I'll be programming that FPGA memory. That is actually, it's a volatile thing. I mean, as soon as the power goes off, that FPGA will be blank. Like I mean, it does not have anything. It's a SRAM is like volatile, right? As soon as power goes off, everything will be erased. So each time we have to keep on loading that value. So JTAG based program only during debug, in the sense like through tools, we will be programming that bit stream via JTAG, and FPGA will act like the circuitry you want. But in the real time as a product, that bits has to be retained, right? So then a flash will be there in the board. So we will be updating that flash. During each boot up, the bits will be fetched from that flash and the circuitry will act like the way you want. Okay. In general, where all these FPGAs will be used? The telecommunication like 5G, 6G, wherever. I mean, like the telecommunication application where the uh, uh, limited number of quantities of the systems will be designed. So there we will be using military application, or I can say all the military application and space applications also, like your satellites. Everywhere this FPGA will be there, because whenever I say that like maybe like Starlink recently, like one of our project customer was for like Starlink, right? So there, I mean, they, if you see, I mean, whether they launch something like thousands of what you say rockets in some few days? No, right? It's maybe like in a year, maybe they'll be launching maybe 10 to 15 systems. So in that case, I mean, it's unnecessary pain to design entire ASIC and fabricate it, right? So that too, like if that does not work the way they want, I mean, it's a waste of money. I mean, they cannot afford to fabricate everything. So they're all, we use FPGAs. I mean, so all high-end applications, right? We use FPGAs, and these industrial control systems like your oil industry, or like various manufacturing, large manufacturing plants, electricity generation plants, their control systems, all control system. This is something like not a predefined thing, right? So whenever I say Snapdragon, 5 million or like 10 million mobiles what they produce, everything will function in the same way, right? But whenever I say a industry based system, each industry will have its own application. For instance, one power industry will have, a power generation industry will have their requirement, and another power generation industry may have different environment condition, they'll have their own different requirement. So in that case, I cannot go for like, I cannot say that like this is the ASIC for, this is the solution, or this is the medicine for all the solutions. So in that way, we want configurability, right? Nowadays, what they are doing, right? So this also is a new trend. They call it as a eFPGA. What they do, like Snapdragon or Exynos, whatever the processors we have, there they put a small FPGA core, right? So what they do actually in that FPGA core, if they want to implement some configurable functionality, right, they are putting that configurable functionality into that small core. That we call it as a eFPGA. In the sense, even the processor itself, we can have one FPGA, right? Fixed ASIC. In that ASIC, we will have small FPGA. Whatever the algorithm we want to put, that is going to upgrade or update over a period of time, right? We'll put those things in the small eFPGA, so that in the future they can upgrade the way they want. That is also a very interesting field actually. I mean, that's evolving. Now people are talking about open FPGA, open source like RISC-V. They are planning with the open FPGA, where it's an open source FPGA architecture. Anybody can manufacture FPGA. So this is evolving field. I mean, still unexplored, still a huge market potential, right? So I mean, AMD will not blindly acquire some company, right? So they, if Intel and AMD acquiring the FPGA means they know the potential of it. And you just Google like all the search engines, like your Google search engine, Microsoft Bing search engines, in the background this search engine will be accelerated using FPGA itself. Like your NSE, if anybody interested in stock markets, right? So there in the stock market, each orders will be executed on the FPGA itself because of its latency requirement, right? So these are all the application actually, like video processing. So nowadays, like we talk about ADAS, LIDAR and all, right? So it cannot be like something like a small ASIC which can handle all this high-end signal processing. There will be FPGA. High performance computing like server, like our data processing, CNN, all these things uses FPGA based systems. So the course plan, I'll just outline how, what are all the things we are going to study in the course. So this course is divided into actually 50 hours. Okay. So initially, is it visible? The font is fine for everyone, or is it too small? Students, are you okay with this font?
Yes, sir. It's visibly.
So initially we will be understanding like this programmable logic gates. So in the sense like when I say FPGA, it's not only limited to FPGA. There are some sub devices as well, CPLD, PLDs, and all, right? So initial 2 hours we will be talking about that various subdivisions of these programmable logic gates. Then we will see what are the various FPGAs available in the industry. So see, actually, like studying only Xilinx FPGA or studying only Intel FPGA, that is not sufficient right now. Many companies will use their own FPGAs like lattice FPGA, microsemi FPGA. If you go to the space industry, it will be used. It will be using some micro semi FPGAs because of radiation tolerance of that FPGA. Because when you actually like go to space, the space radiations will affect your chip, right? So I mean, it is going to erase the content of your flash. So there you should have some radiation tolerant FPGAs. So we will be studying various FPGA device families like Xilinx, Intel, and what all the other families are available. Then we will be moving into Vivado. Vivado is one tool set where we will be designing all our actually FPGA based tool flow. In the sense like this FPGA also has synthesis, placement and routing, and bit stream generation, like same as your physical design flow. So but in the physical design, what you do, like most of the things you do manually, right? So you have to take care of like design this transistor, and there will be some libraries, but still most of the things you have to take care manually, right? So even the tool automates it, but here most of the things you have to tell via some xdc files, that design constraint file. The tool will take care like how to place and route things like that. But when you see a timing violation, congestions, all these things, then you have to manually intervene, and like you have to see like why that error you are getting, and you have to modify it. Okay. But that too, I mean, many people will think that's a simple task, right? But it's not simple task. So the way you have way you write the RTL, that decides actually like how it has to be placement and routed, and also how you give the design constraints, that is also very important. So we will be discussing about that Vivado tool flow, how that Vivado will be used for your placement, synthesis, routing, bitstream generation, all these things. Then we will come to the Intel Xilinx as well as the Intel FPGA. So how this lookup table, I was giving you one example, small example of 2-input lookup table, where I shown you like how lookup table will be used as a circuitry, right? So we will be seeing like that same lookup table, how it will be used as a like, so that circuitry what I had shown was a combinational logic. There are something called shift registers also, right? So that is not a combinational, it's a sequential logic. But this lookup table also can be used for the sequential logic. So we will be discussing about like those lookup table. And whenever I say a design, any design, digital design, just logic gates are not sufficient. We should also have some memories like block RAMs, right? Flash, all these things. So this lookup table also can be used as a memory. So that we will be discussing. So how the flip-flop latches and all will be inferred in the uh, uh, FPGA we will be discussing. Then what are the different memory resources available in the FPGA, right? That we will be discussing. So BRAM, URAM, that is ultra RAM actually. So if you want to go for a very high speed designs, I mean, I was saying you in NSC, BSc, like how they use it for the, actually not only NSC, order execution. Okay. So there are some companies, if you see in the LinkedIn, there are openings in the JP Morgan, Goldman Sachs, Alpha Grep. These are all financial industry, but still they have FPGA opening. That is because they will write this trading algorithm in the FPGA so that it can be, see, even a nanosecond or millisecond delay in the latency, they'll, it will make loss of few millions for them, because their orders will be like in the millions or billions, right? So they use FPGA so that their orders will be placed within a short period of time, right? So even the ADAS nowadays, so ADAS, like your Uber autonomous vehicle or like Apple autonomous vehicles, Tesla, so the decision has to be like within a millisecond or nanosecond, so that it will not hit I mean, it will not end up into any accident. So that is not possible with respect to GPU or CPU, right? So then they use FPGA based designs. So then we have like for the DSP performance, So you need not actually, like in certain computation, let me consider like if you want to multiply two floating point numbers. So usually, like if you go for the conventional logic design, it's a very complex. So we have something called DSP48 core, where multiplication, division, everything, right? So that core will take care, like how processor will have a work, right? So you need not much bother about how to implement those algorithms. So that we will be discussing. Then various synthesis techniques in the FPGA. So you have written a VSDL or Verilog code, simple VSDL or Verilog code. Then how do we design, how do we map that into actual FPGA, right? So that synthesis, elaboration, cross probing, how do we do that synthesis in the Vivado tool? There is something called attribute. So how do we use that attribute for like, so actually, like, see, physical design, you manually control that, right? So here using some attribute, we can actually control how it places and routes that design, right? So into the device, so that we can control. So that attribute will be controlling. So then again, timing constraint, static timing analysis, timing and analysis of the various reports, what all the violations have occurred, that we will be discussing. Then IO resource. In the physical design, you have seen how do we design various IO pins, right? So you might have seen that, like buffers, IO delays. So here also in the FPGA also we have to take care, because this is also kind of like device, actually like act like some chip, right? And once it is programmed. So we'll be discussing about the various IO pins, how to handle those IO pins, SerDes, how to handle SerDes logics, IO delays, all these things. So synthesis is different, implementation is different. Synthesis is actually like whatever the RTL you have written, that will convert it into gate level. Still, it is not mapped into FPGA resources like lookup table and all. So whatever the Verilog or VHDL code you have written, it will actually like generate equivalent gates. That's it. That gate, next job is we have to map into actual FPGA. That will be done in the implementation stage. So in the implementation stage, we will understand how it will be done in the Vivado tool. Again, after synthesis, we'll have combo delays and things like that, based on clock constraint what you are given. But we haven't actually analyzed based on how it is mapped into FPGA, right? So once it is mapped into FPGA, we have to consider actual device routing delays, right? So that will be discussed here, timing analysis with respect to implementation, all these things. So that will be discussed in the implementation thing. So IP, again, you guys might have seen that, like we need not develop each and every component again and again in the ASIC or PD also, because already libraries are available. In the same way, in the FPGA also we have various libraries. You need not design circuitries again and again. For instance, if you want to implement one Ethernet, so we know that like in the FPGA, many companies are using Ethernet. So based on that, Xilinx or Intel, they have come up with their own IP, so that like user will feel, I mean, user can reduce that development time. So here actually, like I'll show you how to integrate those IPs, already existing IPs, and you can build your systems. Okay. And clocking device, I mean, various clocks will be there from the external. So how to divide that clock and use it in your device. Then design constraints. So I was mentioning about like in the placement and routing, we have to control by giving some inputs to the FPGA, like how to place and route. Everything has to be controlled using some input. So that will be controlled via Xilinx design constraints. So that is with respect to Xilinx FPGA. But actually, in general, if you go to the other FPGA like Intel FPGA or uh, Lattice FPGA, they use SDC, that is called Synopsys Design Constraints. So that's SDC you might have used if you gone through ASIC flow. There also we should mention various constraint using SDC, right? So that same thing we are using in the FPGA also. So it's actually like same, one and the same. And I was mentioning here, FPGA is not only a chip level, it's a system level. So once it is deployed into system, if you want to analyze how it is working, how it is performing in the hardware, then we need to analyze using some debug probes. So we'll be understanding how to debug in the hardware itself. So general method, you may say that like you can use some oscilloscopes or signal analyzer or spectrum analyzer. But there are tools in the Vivado or Intel based IDEs where you can actually like using some JTAG what is happening internally, right? So internal to the FPGA you can analyze easily. So that we will be studying in the debugging using FPGA. So next we will be understanding So you can any questions so far? So if you didn't understand any flow or anything, right? So if you have any doubts in the concept what we are covering, you can just interrupt me and ask. Any doubts so far? Questions so far? So today's session is basically, it's a doubt clearing session only, like what you will be studying. So so if any questions, doubts, misunderstanding in the FPGA, you can ask here. Cool. So we will go to the next topic. That is actually next we'll be studying about embedded system using microcontrollers. So in the FPGA itself, right, there are processor cores like RISC-V, or maybe if you want to put ARM. So you can instantiate those core and you can make that FPGA work like a processor itself. That we say the embedded system design. So I'll just show you. It's like very short session where I'll be showing that how we'll be like instantiating those core and like simple LED blinking examples and all. Like I'll just show you using how C program can be deployed onto the FPGA, right? So that I'll be showing. So nowadays, right, the systems will not be just FPGA. I was telling about eFPGA concept. So there is something called RFSoC, or we say VTs, or we say Zinc SoCs, where processor plus FPGAs are coming nowadays. The system on chip based architecture. So because in the FPGA, if they want to run some operating system, then it's not actually straightforward, right? So for that purpose, they actually put some processor so that like they can run the operating system also. That architecture, one of the architecture, like in the, if you go to the Altera based FPGA, that is Intel based FPGA, there you see Cyclone, Aria 10, Agilex, Statix, all these FPGAs. But in Xilinx based FPGA, usually it's a Zinc SoCs, Zinc Ultrascale, Zinc RF SoCs, all these things. So that Zinc architecture we will be discussing, because why I'm stretching mostly on the Zinc is because market share of the FPGA, right? Xilinx in general, market share of Xilinx FPGA is more compared to all other FPGAs. So more than 50% of the market is occupied by Xilinx FPGAs. That's where like I'm covering most of the. I mean, if you come to the industry also, many people will ask the familiarity in the Xilinx based FPGAs rather than Intel based FPGAs. So that's where like I'm covering mostly on the Xilinx based FPGAs. So in that, like we will see some examples like GPIO, UART, and some Ethernet examples, how we can transact using Ethernet, how we can implement UART on the Zinc SoCs. That example we will check. And finally, once that is done, once we understand the entire FPGA design flow, then we will start understanding about the how we can actually like that is actually more than 25%, again almost 25% of the time we will be discussing about how we will be preparing. I mean, what kind of expertise or questions usually we will be seeing in the FPGA based interviews. So that we will be understanding, like recap of the FPGA concepts what we have studied, and like in terms of interview perspective. So we will be discussing that, and Verilog also, Verilog or VHDL people will be asking for the FPGA engineers, that we will be discussing. And when we say FPGA, little bit of the protocol knowledge also is very important, right? So that also we will understand, like what various protocols like UART, SPI, what kind of questions you will be expecting as a FPGA engineers in the interviews. And STA is very important. I mean, if you go to any FPGA interviews, right? So see, actually in the ASIC, you have a lot of flexibility. Wherever you want, you can place and route. If there is any any timing violation, you can actually adjust the placement and routing. But in the FPGA, it's very complex because all the logic gates are already fixed. You cannot move here and there. With the given real estate, you have to build that. So it's something like you can think of, you have given with 1 acre in the ASIC, you can think of you have given with 1 acre land, and people will ask you to build one house. Or in the FPGA, they will give you some 1 or 2 cents of land, they will ask you to build some 2000 square feet. So what you have to do, you have to be carefully planning that design, how to build the house, and you have to build the house. So that's the scenario in FPGA, because it's a limited space. When I say FPGA, if I say 10 kilo logic gates are there in the FPGA, you have to write a RTL such a way that that will fit within a 10 kilo. So if that is not fitting within a 10 kilo, then you have to go to the other FPGA itself. There is no other option, right? So you cannot push, make that entire thing fit into that. You have to optimize that algorithm, or you have to change the FPGA itself. That's a objective. But in the ASIC, that's not like that. So you can slightly change the chip size itself, right? So I mean, you can request that like these gates are not fitting within that, so you can change the chip size itself. That flexibility I do not have. So when I don't have that flexibility, that logic cells can be placed anywhere for a given circuit. So when we have like more path, so critical path will be longer, so more timing violations. So here like timing closure is a big challenge, right? So that's where like we'll be more emphasizing on timing closure here and there whenever we discuss, right? So we'll mostly emphasize on the timing violation, because in the industry also you will face this issue. So here actually we have to plan that. And finally I'll show you some coding examples. Usually like how in the interview they ask what kind of code they'll ask, right? So one thing here you should understand, so in ASIC flow there will be separate STA engineers, there will be separate simulation verification engineer, there will be separate physical design engineers, um, there will be separate test engineer. But as a FPGA engineer, right, so everything you will be doing by yourself, like from the stage you are writing RTL to bit stream generation. Because here like at some stages, like in the physical design and all, it's not that complex as like how you do it in the ASIC, right? So it's a actually it's a very simple flow where most of the things will be taken care by tool. So that's where like industry expects you to be like end-to-end FPGA engineer, not something like FPGA physical design engineer, FPGA synthesize engineer. It's not like that. So you'll be designing the RTL basically using Verilog or Vivado, and they'll expect till the bitstream generation and testing it on the hardware itself. So that kind of expertise usually we expect in the industry. So that's what actually like you have to be thorough with. Like when we say FPGA engineer, you are not limited to certain field. It's that's why I like more on the FPGA rather than ASIC or any other domain. I mean, I'll work, I'll be getting end-to-end opportunities to understand the entire system. Like the time I get the specification from the customer till I deliver to the customer, I'll be working for the full flow. That's where like it's a very interesting, right? So I mean, you imagine that like 5G entire system before it gets released to the market, you'll be like seeing that 1 gigabits per second the data rate, everything on the station itself. So during our initial days, we had seen that like the 5G mobile itself was not there. We were actually, when we were testing that initial 5G protos and all, so we used to test it that base station. Like it's seeing that future before it getting released to the customer itself. So that kind of wonderful products you will get to involve if you learn FPGA based systems. I mean, just an example is like you just go to the LinkedIn and search FPGA engineer. You will see the openings which are like system companies like Hughes. Hughes is basically like they are working for the satellite internet, like how Starlink is working. And you can see openings in Samsung. You see, actually, Samsung usually for the FPGA engineer, Samsung research they'll hire, because Samsung Research who works on this network side, not on the mobile. SSIR basically they works on the what do you think? No questions? Students, am I audible?
Yes, sir, you're audible.
Yeah. Doubts or questions about the sessions, what we are planning?
Sir, do we need to have a very good knowledge about this coding and all?
Actually, some basic of coding is it's required in terms of Verilog or VSDL. Yes, it's required. Little bit of knowledge is required, but on that also we are planning some sessions. Actually, like if you are feeling difficulty in Verilog or VSDL, right? So we will plan some sessions for that as well, so that like you will get some understanding about VSDL and Verilog also. Because when we say FPGA engineer, you will be designing these circuitries, right? So for that, you need to know that VSDL or Verilog.
Okay, sir, thank you.
But wherever is required, I will be also covering those bits. I mean, in bits and pieces. Others, no doubts. What is your opinion? Actually, like, do you feel that like you can manage this compared to your physical design? So what you have gone through. So can you relate that here in the FPGA also? Do you feel that you can manage?
Not sure about the coding, sir, coding part, but apart from that, I think it will be manageable.
Coding part, we will make sure that like you will, I mean, because see that it's again, see it's not that extensive coding also, right? So still you can manage. Actually, it's not, see it's not something like your C programming, right? So Verilog is something like it's like straightforward, like how you design any circuitry. So what about others? Please respond. Actually, like what you feel.
So we can manage.
Okay. uh, what about others? Mm-hmm. Mahesh is saying we will try to manage.
Sir,
Yes, tell me.
uh, sir, am I audible?
Yes, yes, you're audible now. Tell me.
Sir, is this a 2 months course or
Yes,
else how
yes.
many months it takes to?
It's a 2 months course. We are trying to close this in 2 months, actually.
Okay, actually it was mentioned in this website it is 6 months course, right? So I'm just
That actually
thinking how
that
come
six.
it can.
Yes, yes. Actually, that 6 months, right? So that is almost like we are trying to fit it in 2 months, actually.
Okay, okay. Okay, thank you, sir.
Yeah. Also, I think like actually, you can check with the admin also. You will get some e-learning accesses also. And one more thing, we have the hardware, like whatever I was mentioning as a system, you can get a hardware, right? So we have zinc based SoC board in the lab. You can remotely, like how you access your physical design tools and all. So here also you can access that board remotely, and you can work that on the board, like how you want to see, like how exactly it's working on the board. All these things you can check it on the board also.
So which boards we are using, sir? Jin boards
Z
or
board, we have Z board. Z board.
okay. Sir, is this going to be offline or online?
Uh, it's a online course, not recorded. It's a live online course. It's not a offline.
Okay, thank you, sir.
It's not recorded. It's a live class only. It through Google. I mean, our go-to meeting.
Sir, do you will not get the recorded videos?
Yes, I think you are going to get. I think admin can clarify on that. You can check with the admin. So you're going to
Okay.
get the recorded videos. You will get the recorded videos.
Okay, sir. So from
Any other?
when we'll be starting with this?
On that scheduling, you can check in the institute. So I am not aware of the scheduling.
Okay.
So I think as soon as possible. I think this week itself we are planning. So, but you can actually like check with the scheduling part with the admin team.
Okay, sir.
Yes, if you are in PD, it will be helpful. Yes, actually, like see, it's something like what you can say. uh, it's actually like I mean it's not completely like ASIC flow, right? So ASIC PD is a ASIC flow, but here it is something like FPGA flow. So it's like product development. So whatever the knowledge you have learned in the PD, that is definitely helpful for here, right? But it is, I can say that like whatever the PD domain and FPGA is completely different. Okay, so the knowledge what you have studied PD is definitely it's helpful, like static timing analysis, analysis, and there is something called P block analysis here. So that all like same thing like what you have studied, like the DRC things and all you have studied in the PD. But this FPGA is completely different flow compared to your ASIC flow, right? So in that way, actually, like it's a different actually.
So will there be STA class in with respect to front end in this course?
Yes, yes, yes. It will be there. Static timing analysis will be there. Any other questions?
Yes, sir. So,
Yeah, tell me.
like in growth basis, how it could be different from PD? Means how difference is there between PD and FPGA?
Yes.
I'm
So
talking about
actually, like,
future
see,
aspects, like on growth basis. Hmm.
growth basis, right? So see, in the physical design aspect, I mean, when we say that like you are advancing, uh, it's something like we'll be learning the techniques of like maybe how the nanometer technology is improving, right? So with respect to that, we will be like actually like learning different techniques. So and that too, it's like on the large scale you are working. I mean, there is a competition is too much, right? So I mean, there are many people who are doing that PD course, and like it's something like, see, whatever the skill you have, that is like, I can say like everybody possesses that. But in the FPGA domain, what will happen? So for instance, like if you get into in my case, I'm a wireless FPGA engineer, in the sense I develop various wireless algorithms on FPGA. So you'll be building your portfolio in such a way that what kind of domain you are expertise in, like video processing FPGA engineers, or I can say like the knowledge with the protocol FPGA engineers, like companies like Cisco, Juniper, Radisys, Honeywell, Comscope. All these guys are working on the network side. So you'll be developing those skills, actually skill sets. And once you develop those skill sets, right, so there will be plenty of opportunity on that field itself. So for instance, like if you are in the FPGA itself, you are good at some prototyping, ASIC prototyping. So in that itself, you can build a portfolio, right? And one more thing, once you gain expertise in FPGA, right? So FPGA engineers also will be hired as a ASIC front-end engineers, right? So you have multiple options there, right? And one more thing, the growth wise, I was mentioning, so now FPGA is being used in like most of the high performing computing, like your ADAS, like data analysis, machine learning, all the high performance computing. That's where like it's a huge growth, and like there is limited FPGA engineers. And the thing is, like, one thing you have build a portfolio out of it, like the way what are the different projects you do, right? So I mean, in the PD you can claim that like you have worked on these nanometer technologies only, but here you have to build a portfolio, like what are the different protocols you have worked, what you have implemented on the FPGAs, what are the different algorithms you implemented on the FPGA. And I mean, there are like many people will be like hesitating that how I can actually like build that algorithmic development skills. See, FPGA engineers will not be designing those algorithms. Those usually will be designed by system engineers. So your work is basically to implement that algorithm on the FPGA. So you have to write some Verilog or VHDL RTL for the equivalent system architecture, block diagrams or microarchitecture, what they have designed. So everything they'll be mentioning in terms of gates or like some blocks. So that you have to convert into RTL and you have to implement it on the FPGA. So if you become expertise in that particular domains, right, so there is a huge growth potential. So my complete, like from past 10 plus years, I'm working only on the wireless domain, like 5G, CDMA, GSM, smart antennas, right? So I mean, my portfolio is wireless FPGA. I know a few people who are working on the memory controllers. So their portfolio will be like, you have to build in that way. You should not be like FPGA also. Once you get into FPGA also, you should not mess up your portfolio. Like you should not, once you are in the wireless domain, once you are in memory domain, once you are in like video processing, you should not do that. Like you have to stick on to one field. Like the FPGA designing technique is same. See, actually, like it's not like once you build a portfolio in wireless, you cannot get into video processing and all, because technique is same, but it will be add-on thing, right? So once you know that like how to implement various video algorithms, once you know various techniques, so your value will be more. You'll become a field expertise. So in the industry, it's not that like your experience counts, your field expertise will count, right? So in PD also, what will happen actually, like once you become expertise, right, so eventually after over a year, so same thing even the fresher can do, right, the same skill, because like it's almost same thing you will be repeatedly doing. But in FPGA, as you uh, grow in the industry, you'll be like your portfolio will be keep on adding. You'll be working, you might be working on the multiple protocols, you might be working on multiple algorithms, right? So actually experienced FPGA engineers is preferred rather than freshers there at that point, right? So initially, like it will be learning curve, maybe like 4 5 years. Then once after 4 5 years, you're demand will be high because like you have learned that like the skills, the coding skills, or like the implementation skills, the timing closure skills. It's all experience, right? So that experience counts a lot actually.
Okay, sir.
Did I convince you, or you have still doubts?
No, I got it, sir.
Any others? So if no other questions, then shall we end the session? If you have any questions, you can please ask me, or we will end the session. So I mean, you can check with the admin for the actual session plan. So we'll be I'll be looking forward to in that sessions actually. Okay. Hope there is no other questions. So if any questions, you can revert to admin. So he will revert back to me. So okay. Okay. Thank you. Thank you.
Thank you,
Thank you,
sir.
sir.